Mhm. Wow. Hello, everybody. Good to see such a nice group coming together. Um, I know it's 4 o'clock and we normally start at 4 o'clock, but let's wait just a few moments for a few more people to come on board. Okay. We're very excited about this presentation today and topic. Um, I see Miss Pigs is with us. Hello.
Hello, how are you?
Good, good. How are you doing?
I'm doing well.
Good. Very nice. We'll wait just a little bit, okay? I want to see about more people, give more people a chance to get on board before you start, okay?
Okay, no worries.
Is Dr. Turan on board here? Because I was going to ask him.
Not yet.
I don't see him. Okay. Mhm. Mhm. Well, I think we can go. Miss Pigs, are you okay if we get started now?
Yes.
Okay. So, hello, everybody. Glad to see you on board. Got a wonderful presentation today. And this is one of Dr. Turan's students. And I was going to have Dr. Carlos Turan introduce you, but so if you, I will go ahead and let you get started. So today, it is a real pleasure to have one of our computer information science students and presenting today on this is a very, very important topic, by the way. It's hitting all over. Uh, the we're talking about cooling, but these AI data centers are going to be huge. Well, they are huge, and they require huge, huge amounts of power. One of the things that has been over the news recently is that the federal government is building a huge data center in North Dakota, and the amount of energy being used for that particular federal data center, as was indicated on the news, that is more than the amount of energy used by the whole state of North Dakota. So anyway, so Ms. Pigs, would you please go ahead and introduce yourself, what year you're in, your major, and you have a very interesting title. So I'll let you take over. Okay. Thank you.
Okay. Hello, everyone. My name is Mariah Pigs, and I am a sophomore information technology student. And today I will be talking about the different cooling methodologies in AI data centers.
And I think you can share your screen. You should be able to. Do you see you do have facility to share your screen, Miss?
Yes.
Okay, go ahead.
Okay, give me just 1 second here.
Sure.
Can you all see my screen?
Oh, yes.
Yes.
Uh-huh. I
Yeah.
see it.
Okay. Before I begin, I'd like to start with a quick question. Many people know that artificial intelligence requires massive amounts of computing power. But show of hands, how often do we think about the cooling systems needed to keep those machines running safely? Rarely, often, sometimes, or never. As, A- as AI workloads continue to grow, the heat generated by high performance computing is increasing dramatically. Managing that heat has become one of the most important challenges in modern data center designs. This presentation explores several cooling methodologies used to address that challenge and compares how they perform in terms of efficiency, scalability, and environmental impact. So the problem, artificial intelligence workloads are increasing rapidly, and this growth is generating significantly more heat inside modern data centers. AI systems rely on GPU-dense clusters that consume large amounts of power and produce far more heat than traditional computing infrastructure. As a result, cooling has become a major challenge, with some AI data centers using up to 40% of their total energy just for cooling. Traditional air systems, which rely on chillers, raised floors, and air hanging units, were not designed for these extreme thermal demands and are beginning to reach their practical limits. My interests. In addition to examining the broader cooling challenges created by AI workloads, my research also focuses on how different cooling approaches can be evaluated in a consistent and unbiased way. To do this, I compare each cooling method using several key performance criteria. First is rack level heat removal capacity, which measures how effectively a system can remove heat directly from high density computing equipment. I also evaluate power usage effectiveness, or PUE, which indicates how efficiently a data center uses energy overall. Another important metric is water usage effectiveness, or WUE, which helps assess environmental impact related to water consumption. Finally, I consider operational factors such as footprint efficiency, maintainability, safety considerations, and the ability of each system to scale as AI workloads continue to grow. Why this matters. Cooling has become one of the most significant operational challenges for modern data centers. In some facilities, cooling can account for roughly 30 to 50% of total energy consumed, which means a large portion of energy used in AI infrastructure is not going directly to computation, but to managing heat. When cooling systems are inefficient, this increases operational costs and also contributes to higher carbon emissions and greater water consumption. At the same time, AI training workloads are driving much higher rack densities, meaning more computing power and more heat are concentrated in smaller physical spaces. As AI adoption continues to grow across industries, scalable and efficient cooling solutions will be essential for maintaining both system performance and long term sustainability. The societal and environmental problem. Cooling creates environmental stress at both local and global levels. Cooling infrastructure and modern data centers creates environmental impact in both local and global levels. One major concern is water consumption. Some large data centers can use hundreds of thousands to millions of gallons of water each day for cooling operations. So to put that in perspective, we would need 5 Earths to support that. In areas that already face water stress, this can place additional pressure on local water supplies. Another issue is energy consumption. Cooling systems can account for roughly 30 to 50% of a data center's total energy use. When this energy use comes from fossil fuel sources, it contributes to higher carbon emissions and a larger environmental footprint. There are also concerns about certain cooling fluids that contain PFAS, which are known as polyfluoroalkyl substances. Those are often called forever chemicals because they do not easily break down in the environment. PFAS can accumulate in soil and water and have been linked to environmental contamination and potential health risks. At the same time, AI adoption is accelerating rapidly. AI systems are now being used to generate images, large language models, and even full video content, which requires extremely high levels of computing power. As these workloads grow, they increase both energy and water demands, raising questions about responsible AI use and infrastructure design. Because of these challenges, cooling is now becoming a major environmental design issue for next generation AI facilities. Developing more efficient cooling systems can help reduce emissions, protect natural resources, and support more sustainable AI development. So here I want to go over some statistics. So this highlights the cooling share of power usage in AI data centers. As you can see, data centers use about 1.5 to 2% of global electricity. That's a lot of electricity. There are over 8,000 data centers worldwide, including 2,700 of those right here in the US. AI driven data center electricity use could reach 8% of global electricity by 2035. And a single hyperscale data center can use 3 to 5 million gallons of water per day. Another statistic that I would like to point out are the thermal trends. Rack power density is now 80 to 120 kilowatts for AI racks. Again, a huge amount of power being used. Cooling energy is up to 50% of total facility load in AI clusters. Growth drivers. Model size and compute doubling every 6 months. The direct cooling adoption growing from 5 to 25% of new builds and increasing regulatory pressure to phase out PFAS chemicals. Cooling methodologies. This section introduces the main cooling methodologies currently being used or explored in modern data centers. Each approach manages heat from high-density computing systems in a different way. I compare 4 primary methods: traditional air, direct liquid cooling, immersion cooling, and hybrid or emerging cooling architectures. The goal is to evaluate how each method performs in terms of heat removal, energy and water efficiency, scalability for AI workloads, and overall environmental impact. The first, I'm sorry. The first methodology that I will be talking about is air cooling. Air cooling is the most traditional and widely used cooling approach in data centers. It works by circulating chilled air through the facility using systems such as computer room air conditioners and computer room air handlers. The cool air is directed towards server racks to absorb heat and then removed through airflow management systems. One of the main strengths of air cooling is that it has a relatively low upfront cost and is already widely supported by existing infrastructure, which makes it easier to implement and maintain. However, as computing density increases, especially in AI data centers that rely on powerful GPUs, air cooling begins to struggle to remove heat efficiently. These systems also tend to consume large amounts of energy and require significant physical space for airflow management. Because of these limitations, traditional air cooling is generally better suited for legacy data centers or lower density computing environments, rather than the extremely high thermal loads generated by modern AI workloads. The second and third methodologies that I want to go over are liquid cooling and emergent cooling. Direct liquid cooling and emergent cooling are 2 advanced approaches designed to handle the higher thermal demands of modern AI data centers. In direct liquid cooling, liquid is circulated through cold plates that are attached directly to high heat components, such as CPUs and GPUs. Because liquids transfer heat more efficiently than air, this method can remove much more effectively and support very high rack power densities, sometimes exceeding 80 to 120 kilowatts per rack. This leads to higher thermal efficiency and can reduce the overall power usage effectiveness, or PUE. However, there are still some challenges, including the need for specialized infrastructure, potential leak risks, and the use of engineered cooling fluids, some of which may contain PFAS-based compounds. Immersion cooling takes a different approach by fully submerging servers in a dielectric electric liquid that absorbs heat directly from the hardware. This method offers extremely high heat removal capacity and can be very space efficient while also operating quietly. It can also extend equipment's lifespan because components experience more stable thermal conditions. However, immersion systems can be expensive to deploy. require specialized tank designs, and raise concerns related to fluid disposal and environmental impact if the cooling liquids are not environmentally friendly. The next methodology and final that I'm going to go over is hybrid and emerging cooling. Hybrid and emerging cooling architectures combine multiple cooling strategies to improve efficiency and sustainability in AI data centers. Instead of relying on a single method, these systems integrate approaches such as air cooling, liquid cooling, and advanced heat exchange technologies to better manage extremely high thermal loads. For example, some facilities use mixed air and liquid cooled racks, while others capture and reuse waste heat generated by servers for nearby buildings and district heating systems, or even agricultural applications. Some emerging designs also incorporate renewable energy sources and explore PFAS-free cooling liquids to reduce environmental risk. One of the main advantages of hybrid cooling architectures is their ability to balance performance with sustainability. These systems can support high-density computing environments while also reducing water usage and lowering overall carbon emissions. However, they can be more complex to design and also require higher engineering costs. And because many of these systems are still evolving, there is currently limited industry standardization. For this reason, hybrid cooling is often best suited for newly designed AI-focused data centers, where sustainability and long-term scalability are key priorities. So now we're going to go over a summary of what we just discussed, and as well as my conclusion. So this table summarizes the main trade-offs between different cooling methodologies that we discussed. Air cooling is the oldest and most widely used method because it is relatively inexpensive and simple to maintain. However, it becomes less effective in high-density computing environments because air cannot remove heat as efficiently as liquids. As AI workloads increase, rack power density, as AI workloads increase rack power density, air cooling requires more energy and larger physical infrastructure to maintain safe operating temperatures. Direct liquid cooling offers higher performance because liquids transfer heat much more efficiently than air. In this context, high performance refers to the ability to remove larger amounts of heat from high-density computing equipment, allowing data centers to support powerful GPUs and AI training workloads. However, liquid cooling systems require more specialized infrastructure and maintenance. Some systems also rely on engineered cooling fluids that may contain PFAS compounds or forever chemicals, like we discussed earlier. Because they do not break down easily in the environment and can accumulate soil and water over time, it becomes a big issue for the environment and our water systems. Immersion cooling provides some of the highest thermal efficiency because servers are fully submerged in a dielectric liquid that absorbs heat directly from the hardware. However, these systems can be expensive to deploy and may raise concerns related to fluid disposal and system complexity. Hybrid and emerging cooling architectures attempt to balance efficiency, sustainability, and scalability by combining multiple cooling approaches and integrating technologies such as heat reuse or renewable energy-driven cooling. While these systems show strong potential, they are still in relatively early stages of adoption and require more complex engineering. Overall, this comparison highlights the trade-off between simplicity, efficiency, and environmental impact when selecting cooling strategies for modern AI data centers. Now, for me, if I were to choose a system that I think would be the most beneficial out of the four that are the most commonly used right now, I would do hybrid and emerging because of the less of an impact that it has on our environment. but I do feel like there's still room for growth and newer methodologies to be developed. AI growth demands more efficient and sustainable cooling solutions. Air cooling is not suitable for future AI workloads, and liquid and emerging cooling offer strong performance but come with water, chemical, and environmental drawbacks. Hybrid and emerging PFAS-free approaches provide the best long-term pathway for efficiency, scalability, and sustainability. My goal was to identify, compare, and evaluate the safest, most sustainable cooling pathways for the next generation of AI data centers. Thank you so much.
Great. Wow.
Thank
Thank
you,
you.
Ms. Biggs. Thank you.
I'm going to, I see your mentor is available now, Dr. Duran. Uh, and since since he didn't have the opportunity to introduce you, I'm going to let you, Carlos, uh, uh, guide the questions from the audience. Go ahead, Carlos. Go ahead.
Yeah, thank you, Maria, for this great presentation. Again, one more time for your commitment and your time on this research. Actually, I had a question, and one of my questions you already mentioned that what was for you the best, if you need to recommend any of these techniques, what will be that one? Or you already mentioned, but you can extend a little bit more on that.
So the reason why I would choose hybrid is because, again, the environmental impact is far more less than the other three cooling methodologies. Um, Obviously, water and the uses of power are major environmental concerns right now. And I think it's important to choose something and a method of, you know, allowing these data centers to be operational with the least impact on the environment as possible. And I feel like that's what we can, start with.
Right. Yes, I think that even that is the like one of the cons is engineering costs. I think that in long term, right, will
Mhm.
be pay off with the in terms of the environmental side.
Yes.
Mhm. Perfect. So if there is any other questions, I think that this topic is quite interesting because nowadays people are using a lot all these large language model tools, not only to generate text to text, but also text to image and text to video. And I think that many people is not aware, right? The consumption in terms of energy that this technology is utilizing to provide all these response uh, um, in services. So I want to know from the audience if they already, they were aware about these issues, and if you have any questions to Maria, please don't hesitate to ask or provide your thoughts and comments.
Hey, Miss Pix, this was a wonderful presentation, drawing the attention to this really crucial issue. So it looks like we can never solve all the problems because once we solve one problem, we open another one, and it goes on and on and on. So this problem is here to stay. And do you know what? Yeah, you mentioned the available methods to do that, but any long-term kind of modernistic projects or any groups that work on these national labs? Are you aware of any existing projects to resolve this issue? Because together with the AI, we definitely need to take care of this. So how is this currently being handled in terms of science, research, and development? Are you aware of any current projects in that?
I do know that at some labs in Japan, people are currently, testing out the hybrid method, as well as at, I believe it's Purdue University. So I
Okay.
do know that they're working.
Mm. Well, I hope NSF will give some funding for that, to bring the efforts, to upscale the efforts to do that. AI is here to stay too. We're not giving up AI, just the opposite.
Yeah.
And is there anything that, in terms of usage of AI that we can do to use it to be more considerate about the environment and the resources? Yeah, just, we're going to, doing our projects and similarly to the rest of the environment, we rarely think about the consequences. So, are there any recommendations on that? How to be more considerate when using AI?
One thing that we can do is have a plan. If we're going to utilize AI, especially for like our projects that we're working on, like our text-based product projects, I believe that we can have an outline. So that way we're not using an excessive amount of AI. AI is
Mhm.
be used as an assistant, as a tool, not replace what it is that you're trying to accomplish. So I think if we look at it more as like an assistant and not a replacement, we can be a lot more responsible with how we're using it.
Mhm. Makes sense, yeah. Mhm. Yeah. Mhm.
Is there any other questions, any comments that you wants to stand talk?
I had a question. And from your research, did you find out any information on who bears the cost for cooling all these AI data centers?
So I haven't really truthfully done a lot of research about who bears the cost on that. But based on what I have researched, I can only assume that we are bearing that cost.
What I meant was one of the issues that we're seeing is that customers who aren't actually using the data centers but are near to the data centers are having higher electricity rates because of demand and supply issues. And so I might be here in Florida, but the data center is in North Dakota. Uh, they are the ones who are paying a higher price for the
Mm.
electricity. So I don't know. I was wondering if you found out anything else about that.
Not yet, but that's something that I am working on.
And then my other question was, did any of the hybrid approaches mention converting the heat back into electricity? Did you come across any of that way to make it more efficient? So instead of just, dissipating the heat by using the heat?
No, they haven't. And it's very interesting that you brought up that point because it would make sense to be something to do. But the problem is that even if it does convert it back into heat, the problem is the chips that the data centers are, using, they're made out of PFAS. So, once you heat up those chemicals, they're still going back into the environment.
Okay, so it's more complicated than just taking the heat and converting it back. Okay,
Hmm.
thank you.
You're welcome.
Any other questions?
Well, here is a project for our students, using AI to solve the problem with cooling AI, right? And come up with some good ideas that can, why not, be patented later on. So, mm. Thank you, Ms. Pix. This was very interesting. We have to draw attention to those issues more often in our everyday life.
I couldn't
Yeah.
agree more, Nellie. Those are very, very important issues. Like I mentioned at the very beginning, the federal data center that's going up in North Dakota, they've already estimated that it will use more power than the whole state of North Dakota uses now. Oh, that blows your mind. Blows mine. Anyway, wonderful presentation. Thank you so much. Yeah. Any
Thank
final, Carlos?
No, just one more time, congratulations for this presentation. This is a really good research that you brought, and actually the topic was brought from Miss Pix. She was the ones that picked this topic, and then we started like finding a literature review, working on this, and finding the methodologies and what is out there to overcome these issues. So this is a great topic that she brought into the table, and we start working on it.
So, when did you start on the project, Miss Pigs?
So last fall,
Okay.
Okay.
but it was something that has always been a concern of mine, even prior to that. Ever since I first learned about the data centers and like how they operate, it's been something I've been passionate about. So
Oh, great. Okay. What are you're a sophomore right now?
yes,
What do you see yourself doing on after graduation?
continuing this research and hopefully, coming up with a solution.
Oh, good for you. Good for
Very
you.
well.
Thank you now. Thank you so much.
Thank
Thank
you.
you. You have a
Take
nice
care.
day, everybody. Bye-bye.
Okay.